any of your points are missing, then we have a problem. It's really important that you do the mini exercises. I'm gonna start getting very strict about it. If you haven't done the mini exercises, we're not going to look at your code because you're never gonna pass the class if you don't do the mini exercises. So it's very important that anytime you get points for a programming class, we should check it here. My mic should be fine on Twitch. I'm seeing the volume move on OBS. Let me check. If somebody on Twitch hears me. My computer hears me just fine. I'm looking at a green thing jumping around. I'll show you guys. Look here. This thing is my microphone. I sometimes forget it, so it's a very good thing to ask me if it's not working, because it's a Bluetooth headset, and sometimes my computer is like, yeah, I don't need it, so I don't always notice if it's missing. So very important, every time we grade homework, if you get any points, then you go check if your points appear there, because the programming exercises, the ones we grade in class, I type in who gets the points. So if I type in wrong, then they go to somebody else and you need to check them. The mini exercises, they come from this other site here. Passing you guys the link again. So everybody should have done the first 3 by now. If you haven't done them, please do them. They don't close until you have your final exam, but it's a bad idea to do them later on. And after we look at the second chapter, you should be able to answer the next 3, which is this one here, this one here, and this one here. So please try to do those today or later this week. And after you have done those, the explanation of the following homework is down here. After we go through the second chapter, if somebody doesn't know what binary numbers are or what prime numbers are, please stick around so I can clarify those things for you. It would be a good thing if you guys already knew it, but since you're a combination of people from different study programs, not everybody knows these things. So keep that in mind. If you don't know what binary numbers are, and if you don't know what prime numbers are, you have to stick around. So I always ask you guys to look at the book before we have the class. So I'm really hoping you've read from page 35 to page 54 in preparation. We're going to go over the content together and look at tiny little code examples of the stuff we might have missed. So I'm going to skip to page 35, which is where we start today. Still chapter 1, still chapter 1. Chapter 1 is wonderful. There's so many things in it. And remember, whenever you're confused, just start reading again from the beginning. Just read it over all the time. I've read this book like maybe 25 times. I learn new things every time. Okay, so first of all, they're discussing how to name variables. You could use an underscore in variable names if you want to. It's a bad idea to put underscores in the beginning of variable names because you might create conflicts with libraries. But if you really want to make a long variable name, you could use underscores for that. Let's go to my repository. Let's go to chapter 2 and start making our demos. So we're going to make demo 1, agosto-diciembre 2021. Let's make the include that we always make so we can actually print stuff out. Let's make a main. Let's make it return 0, just so we don't have any trouble. We haven't talked about that yet. We'll talk about all of that later on. And then we could make variable names. So we've been making stuff like a is equal to 3 thus far. But if I wanted to, I could make longer names using an underscore if I would like to. Some people like to use the camel case instead, and both are equally readable. It's important that you know what your variables are for. So if your variable has a very short name, it's a good idea to explain in a comment what that value means. so that you won't be confused later on. Some of these words like include, main, return, don't use those as variable names, just as you don't want to use if, else, int, float. Those are reserved words. You do not use those in variable names or in names of anything else. Okay, section 2.2 explains data types. So the ones that are ints, they're going to be integers, whole numbers. We've also been using characters, which is what we were using in the homework. We could put like maybe the letter A, or we could put the carriage return, which is an enter, or then we could do decimal values. We could make a float, or we could make a double. The difference between floats and doubles is that you can put larger numbers in doubles because double has larger precision. It also lets you put smaller numbers into it. I'm not going to take anybody's time explaining floating point numbers at this point. There are very good tutorials about it, but it's a slightly complicated concept. Like, we're not storing these numbers. We're not storing the whole part and the decimal part. We're storing the number as a representation where we have a number that we call the mantissa, which multiplies a base elevated to a power of an exponent. So what we're actually storing is the bits for the M and the bits for the E. And the base is a constant. So this is a standard. It's an IEEE standard on how to store information. And I will link it on Discord so you guys can read it. Single precision is float. Double precision is, well, double. Not all of you have to understand this. If you work with like low-level electronics, or if you're going to be programmers, you're going to have to like truly profoundly understand this representation. The M here, the mantissa, that's the part that's going to kind of like give the numeric value as such. The exponent is going to give like the order of magnitude, and the base is going to determine what kind of numbers you're going to be able to store. Not every single possible real number can be stored in a floating point representation. And what does the floating point mean? Floating point means that since we're varying the exponent, the bits we put in the mantissa, they might be the thousands, they might be the tens, they might be the millions, depending on which exponent we're using. But please look into those pages if you really want to know in detail. Additionally, I could use best specifiers like short or long, meaning that if I want very large numbers, I would want to make a long int. If I know that the numbers are going to be very small, I can make a short int. So I can save space, or I can use more space according to how big numbers I think I'm going to put in that variable. If you want to know how large the numbers can be, the easiest way is to check your reference card. Your reference card will tell you what those constants are called. We have integer type limits. They come from this header file, limits.h, that have the minimum and maximum values, and float.h has the limits for the floating point numbers. You can also check these on a specific machine. They're pretty standard on computers, but if you're working like on a microcontroller or some very tiny thing, there might be slight differences on the ranges of representation. So let me just copy paste that here too, so that you remember that you can test them by using those exact libraries. So just let's make a tiny little test. Let's see what the value is for int max on my computer. So from limits h, I want int max. And I want to print it out. So that's going to be an integer. I need to remember to use double quotes since this is C. And I need to type it exactly like it said on the reference card, uppercase int underscore max. Let's try to compile this file and write it. So my int max is this number here. The int max that they were expecting, it should be at least 32,000, but mine can do larger. So mine's actually the same as my long max would be expected to be. Let's check if there's any difference between my int max and my long max. On most present day computers, ints are always long. On older computers and on limited hardware, they might be different. So let's look at my long max. I can't print a long as with a D. I think I have to print it with an LD. The reference card knows I forgot to compile. Yeah, my long int max is much bigger. Modern computers let you work with much larger numbers. But you have to remember the range of representation is limited and you cannot mix. If you said the variable is going to be an integer, you can only put integers there. If you said it's going to be a character, you can only put characters there. So if you really need decimal values, you need to use floats or doubles. Okay, let's make a poll to see if this is kind of okay. One person knows what's going on. Two people. Well, that's already a pleasure. Talking to two people is much better than talking to myself. Okay, then constants. What's the difference between a constant and a variable? A constant is something you never want to change the value of. So we already learned the last time that it would be better to put those in defines. If I just write the constant like this, it's going to be an integer. If I want it to be a long integer, I have to put an L at the end. If I want it to be an unsigned integer, then I could put a U in front. What's an unsigned? If I use an unsigned version of a value, I get double the range. Why do I get double the range? Computers represent everything with bits. And if I want to include information on whether the number is positive or negative, I need to use one of those bits for the sign. But if I don't need the sign and I tell the program this number can never be negative, then my computer can take that extra bit that was supposed to be for the minus or the plus, and it can use it for more information about the number. So that gives us twice as many possible integer numbers. We're going to look into it in a bit when we talk more about binary numbers. We're going to have to talk about it in a section during this chapter. Okay. Also, when we understand better stuff like octal and hexadecimal numbers, we'll understand this section. But to understand those, we really need to understand the binary numbers. So we're just going to skip a tiny bit here. Read the whole section if you have any questions about this. An important constant that we can learn about here is the string termination symbol. A string termination symbol is used when I want to put multiple characters in a variable together. Like I want to put a word. When I want to put a word instead of just a letter in a variable, I'm going to use the library string to work with those. It's here in our reference card. I will take a screenshot for you guys. So I can work with words instead of just letters, but I need to understand that at the end of every single word, when I close the word, and word here means a sequence of characters, it would actually include white spaces, it's going to have the termination character that's going to be the \0. So the same way as I can check if something ends in an enter or an end of file, I could check if the string ends by looking for the string termination character. Okay, so I could have a string, like here, I am a string or hello world. I can put strings in character arrays. So we could here make a character array. Let's call it line like they do, and then we could give it some length. It's going to be a maximum length here. Let's suppose we can put 20 characters in it. And because we also want to put the termination character, we're also going to always make one more space so we can actually put that information there. So now I could start putting values to it. I could tell it that the first character, I would like it to be an H. Let's put hola in there. Hola. And then I need to tell it that the character, the end character comes after the A. So the string ends there. Why do I need to tell it that the string ends there? If I want to print this string, I don't want to print all of the space that I reserved. That's for 20 letters because I only have 4. So let's print this one. My string is, I use %s for the string. And then I want to print the line. Let's make another terminal for the compilation so I don't have to be closing and opening all the time. So I'm going to compile this demo file and I'm going to print it out. It says my string is hola. What happens if I don't put the termination character? The same thing might happen, but if I've previously stored some other crap in there, let's say that I have some stuff here in further positions along. If I correctly place the string termination character, my program understands that my string ends there. If I do not place the termination character, my program doesn't necessarily know it ends there. Now it still remembers that it ends there when I run it because it's the same memory I've been using before. So let's put stuff there to make it do other stuff. Okay, so now it says hola 1x, and then it doesn't say the y and the z because it's putting the unused positions as if they were string termination characters. So now if I start terminating here at the 5, no, actually, let's not terminate at the 5. Let's terminate at the 4 again. If I don't set the termination there, oh my God, I keep typing the wrong stuff. The C comment is like this. What did I do now? There we go. C comment. It's being so nice to me. When I don't put any values, it takes those as string terminations. Don't count on your computer ever doing that. My compiler is now looking out for me. The computer has no responsibility of putting any reasonable characters in any of the positions you haven't filled. So it's always your fault if some trash gets printed afterwards if you didn't put the termination character. We're going to be running into this in later programs where we actually recycle the memory over and over. What they're doing here is a routine that calculates the length of a string. We could try that now here, since last week we didn't actually have time to look at how to make routines. So let's make our own routine for calculating length. And we're going to give it a character array. Let's call it like they do in the book. So I'm going to use a variable. I'm going to call it L, and I'm going to set it 0. Then we're going to do a while loop like we did last week. We're going to look at while the position I in the string is not the string termination character, we're going to increment the I. It doesn't matter if I increment it after or before, if it's there inside the while, and then we simply return how long was it. So now I could call this to figure out how long my string is. My string has length, it's going to be an integer, length of string, and I want to give it line. So now it should know. I called it first L and then I called it I. This is so typical of me. L, L, L. I want it to be different than in the book, but then I forgot and I want it to be different. Okay, so now my string has length 4 because there's a string termination character in the 4th position. If I just put some other crap there, the length is going to change. And now it's going to tell me that my string is going to have length 6 because my computer is nice enough to put the unoccupied positions as string termination characters. 6. If I put some stuff in position 6 and 7, it's going to start saying that my string has length 9. Let's put some stuff here. Now it has length 9 and it contains all of this stuff. And if I put the string termination character in place, it's going to start having length 4, even though there's stuff later on, and even though it actually has 21 positions, because it's only counting until it finds the string termination character. So that's an important thing to remember. We're going to put it in a poll. Now I made 2 backslashes. I meant just 1. I can't use Discord today at all. Come on. Like this. I meant it like this. It's okay if this seems complicated now. Just remember, whenever something's printing you didn't want to print, you're probably missing a string termination character. And if you're trying to store something somewhere and it doesn't seem to fit, if it says that your index is out of bounds or you're out of memory, you have probably forgotten to contemplate a space for the string termination character. Another thing we're learning in this section is that we can make an enumeration constant. An enumeration constant is assigning automatically numeric values to words you write. So I could, for example, make an enumeration called valor de verdad. And I could say I want it to take 2 values, falso, verdadero. So this means that I am actually creating a type. Where do I put this type declaration? Let's see what happens if I leave it here. It's all very happy. I have an enum valor de verdad. Now, can I use it like this? I would always have to call it enum valor de verdad, or I could make a type definition saying that I want enum valor de verdad be something shorter, like let's say bool, and then I could just make a bool, and now that bool is going to be an enum valor de verdad. So I could make it be false. And this works just fine. So I can kind of define my own types And this is very commonly used for stuff like names of the days of the week or the months or something like that. If I want to print them, they're really just integers. So if I want to print this bool something, I'm actually printing an integer. Let's set it here. My truth value is, and it was called something. And let's see what numeric values it's assigning to verdad and falso, because it's doing it automatically. Compiling, running. So it's 0 when it's false and 1 when it's true. Why is it like that? It's because I put false first and verdadero after. If I change their order and I compile and I run again, it switches around. Now it's 1 for false and 0 for true. It makes more sense the other way around because it's more consistent with how C works. So we're just going to leave it the other way around. Compiling again to make sure I didn't break it. Okay, section 2.4 explains you can combine declarations. If you want multiple things of the same type, you could declare them on one single line. That's entirely fine. You can even assign values to them on one single line. The arithmetic operators, we've already been working with those when we were learning to use the compiler. We can use the plus sign to add numbers, minus sign to subtract, multiply, divide, and then we can use the percent to do the modulus, which is the residue. We talked about it, I think, on the second week. So it gives us the remainder. When you divide x by y, what is left over? These are really easy things to test. And if you wish to test them, you can easily add them to your program. I could add here stuff like integer modulo another integer is the result. And then I can just write the numbers that I want. Like, let's say I want it to be a 15 and a 7, and then I want to see what 15 modulo 7 is as a value. I compile, I run, and I can observe it gives me a 1. Why does it give me a 1? Because if I divide 15 by 7, well, 7 times 2 is 14. So there's going to be 1 left over. And if I change these values, I could put them in variables actually to make my life easier. Let's call them A, B, and C for now. I'm going to call this one other, so I don't have two different C's. I could give them values. A could be 24, 23. B could be, let's say, 4. And C could be A mod B. So now I can just write here that I want to print A, B, and then the result. I compile again, I run again. 23 modulo 4 is 3. Why? I can do this easily by subtracting from 23 the 4s. If I take 1 4 away, I'm at 19. Okay, then I take another 4 away, I'm going to be at, what, 15. I take another 4 away, I'm going to be at 11. I take another 4 away, it's going to put me at 7. I take another 4 away, I'm at 3. I can no longer take a 4 away, and hence I have the residue. So this is an important thing to remember. The percent sign has nothing to do with percentages, it's the residue, also called the modulo. Let's check with the poll. And if you're making complicated calculations, you put parentheses on them so that you don't have to guess what the precedence is. If you, for example, want to do divisions and multiplications and additions all together. Section 2.6 explains us how to compare values, whether something is larger than, larger or equal, less than, less or equal, equal or not equal. So these things, they will give values true or false. True will be a 1, false will be a 0. And all of that information is also contained in our reference card. The comparisons, they're all here in the card. So you never have to remember how to write them as long as you have access to your reference card. So this is relatively easy. So here, for example, we're checking if first I is 0, then if I is smaller than limit minus 1, and simultaneously the character we read was not an enter, and simultaneously the character was not an end of file, then we increment 1. So the double ampersand, it's an and. It's a logical operator that requires both sides to be true for it to be true. Whereas the 2 bars, that's a logical or. If either side is true, then the condition will be true. If both are false, then it will be false. Okay? Check all of this if you have any trouble. If you have a truth value, a 0 or a 1, and you put an exclamation in front of it, that's called a negation. The negation of false is true. The negation of true is false. So you can just kind of like make like, if this is not happening, then do this. And the not, you will make it with the exclamation. Section 2.7 explains to you how to convert from one type to another. They give an example of how to convert things from characters, like letters 1, 2, 3, to a number 123. It's a very good example. I really recommend studying it. And how to convert text between lowercase and uppercase. The text conversion thing, this is a very interesting thing. You guys might not be very familiar with the ASCII coding. In the ASCII coding, every single letter corresponds to a number, and we have a very limited amount of numbers. We could look at those numbers. We had here the character other. We could look at the value of different characters. For example, if I put an uppercase A into other, we could print other as an integer to see what the ASCII code of that letter is. So what I'm doing here is I'm going to print the same variable twice. I'm going to print it once as a character. Actually, I should just put a C here. And the other time, I am printing the same exact variable, but as an integer. So let's compile, let's run. So it tells me that an uppercase A is a 65. Okay. Then let's look at another letter. Let's change the value. Let's look at what a lowercase a would be in the ASCII code. Okay, that would be a 97. And the ASCII code is very nice. Everything comes in alphabetical order. So if I want to know the difference between the uppercase and the lowercase, I could put that in an integer variable. We could recycle our variable a. So I could put here that a is the difference between the lowercase a, which is a 97, and the uppercase a, which is a 65. So now if I want to make other letters lowercase, I could just add them that same difference to make them lowercase. So if I put here, let's say the letter P, and I want to make P lowercase, How do I make P lowercase? Let's try to print first the variable that contains the P. Then we're going to print that variable, but we're going to add the difference between the lowercase a and the uppercase a. Compiling, running. So I have now made a lowercase p by trusting that the alphabetical order in the ASCII code remains the same. So they're using it here the other way around. They're turning from uppercase to lowercase by using the difference. Actually, they're doing the same thing as I am. They're doing the same thing. They're going to lowercase. For some reason, I thought they were going to uppercase. So if I want to do this the other way around, let's say I have a lowercase letter. Let's say I have a lowercase w. If I want to make it uppercase, this thing in uppercase means that I'm going to subtract the difference from it. So I could make from uppercase P a lowercase, or from a lowercase w an uppercase, by using the difference between the two letters in the ASCII code. Okay, we can look at the ASCII code to know what other values do the other symbols have there. And that would make us understand how the conversion between letters and numbers is working. So let's look at this. The stuff we've been looking at is here. Uppercase A is a 65, lowercase a is a 97. So now let's look at numbers. So the ASCII code, let's look at the number 0. And let's look at seven. So I'm looking at the character 7 and the character 0. What numerical values are we going to get? 0 is a 48 and 7 is a 55. What's the difference between 48 and 55? Well, it's a 7. So I can do arithmetic with it. And that's what they're doing in the book. They're looking at the numerical value and then they're subtracting the value for 0. Because if you subtract the value for 0, then you come up with an integer number that corresponds to that. So we could change the second line here. The numerical value for the letter 7 is what? So the numerical value for the letter 7 is the difference between the numerical values of the letter 7 and the letter 0. So the numerical value is a 7. Then when I'm reading a character string like let's say 1, 2, 3, if I take the numerical value of the 1 and then I multiply it by 10, well, then I get a 10. If I multiply it by 10 again, then I get 100. So basically, we could be doing multiplications by 10 anytime we read a letter. So if I read the 3 and I convert it to the numerical value of the 3, okay, I'm fine. Then I could add to that the numerical value of the next letter and the next letter and the next letter. So what are they doing? Let's take a screenshot of the code here. This is pretty ingenious. Let's see how numbers are converted. So we are reading starting from the position 0. If that position is a digit between 0 and 9, then we look at its numerical value and we add it to n. Then we are also adding 10 times an n there. So we first read the first number, like in 1, 2, 3. No, I can't even type, sorry. 1, 2, 3. If we read a 1, 2, 3, we will first get the 1. Then we will multiply in the next turn the existing 1 by 10. So we get a 10, and to that we will add a 2. So now we have a 12. To that 12, we will multiply it by 10, we get 120. To that 120, we are adding the 3 to get the 123. If you don't want to do this by hand, of course you don't have to, because all these routines, the converting to uppercase, lowercase, converting to numbers, everything's already done in those libraries. So if I would want to convert things to uppercase or lowercase, I could use the C-type library. The last 2 things here on the reference card are the conversions to uppercase and lowercase. So we could just use them. And if I want to do conversions from alphanumerical to number, those are also in my reference card. If I could just remember where. Looking for them. I think it's in the standard library. Yes, they're in standard library under conversions. Right here. So there is an A to F, meaning take alphanumerical and give me a float. There's an A to I, meaning take alphanumerical and give me an integer. So we could use those. And stuff like testing whether a digit is between 0 and 9. I'm really sorry about my neighbors. They like revving their engines. You could use the isDigit C to check if a character is actually a digit. So all of this is explained here in great detail. It's really important you read this. Section 2.8 explains the plus plus things. Let's look at the plus plus things. So if I have my integer, let's say it's 17, let's print that same integer many times. I'm going to print it, first just the A, then I'm going to print plus plus A, and then I'm going to print A plus plus, and in between I'm going to print A again. So here, this one's going to be the plus plus A, this one's just going to be an A, this one's going to be just an A, this one's going to be an A plus plus, and then we're going to print just an A again. So we're printing this same variable 5 times, and we're doing twice an operation on them. I lost my little window. There's my little window. So let's look at this stuff here. It's the bottom part because we have tons of code in the same thing. So first, we're seeing that A is valued 17, which is exactly what we were asking it to be. Then, when I do the plus plus A, it prints me an 18, meaning it first increments the value of A and then it prints A. So the next time I print just the A, it's going to be an 18. If I instead do A plus plus, it doesn't show me the 19. It shows me the 18, but the next access to A, it's already 19. So plus plus A means first add 1 to A, then do whatever you were going to do with A, in which case is print it. A plus plus means first do whatever you were going to do with A, which in this case is print it, and then increment it by 1. So it's very important that you think whether you want the effect to happen before or after. It's technically, in both cases, incrementing by 1. The difference is when do you increment by 1. We could do the exact same stuff with the decrements as well. Let's add those here. I'm going to put a minus minus A and an A minus minus. It's going to work the exact same way. I'm sorry, I didn't mean to close that. I meant to use the other window. compile, execute. So we can confirm the same exact behavior for the minuses. If it's put before the variable, the subtraction happens before the printing. If it's put after the variable, first the printing happens and then we modify its value. This is very important. We don't forget this because it really makes an effect in many of the codes. All these exercises here are really good, really, really, really good. And if you get confused with the exercises, it's very easy to find someone on GitHub who has done all of the exercises for this textbook. You would just type GitHub KR or exercises solved. Okay, KR solutions, KRC book solutions, KR solutions, KR exercises. So there's like 500,000 people who did all of these exercises and put the answers in GitHub. So you don't all have to be looking at the same one. That's why I'm not going to link any of them. You can very easily look them up. And if you want to become good programmers at some point, you will join these 500,000 people. You will also do all of these exercises and put them in your GitHub. And believe me, if you're one of those people who really want to work at Google, this is how you end up working at Google. You solve all of these exercises, you put it on GitHub. And you do that with every single textbook you encounter later on. Any reasonable looking exercise, you solve it, you put it on your GitHub. Okay. Now we need to make sure that there aren't any questions thus far, because we're going to get to the more complicated stuff. We're going to start talking about the binary numbers. Let's make a poll. If you're okay continuing to another topic, click on the green thing. If you have a question we really need to answer now before we can continue, the red question mark. If you think you're going to be fine when you read the book later on, the confused face. If you don't really know what's going on because you just got here, the sleepy face. I still have my 2 people listening to me. So for the sake of those 2 people, we're going to go to the whiteboard and we are going to learn bitwise operators. Let's take a little screenshot of them to put them on Discord. And then we head on to the whiteboard. Okay, first, binary numbers. In your computer, all of the information that's stored is stored in binary. It's not stored in any other way. So if you want to store, let's say, the number 30, there's not going to be a 3 and a 0 anywhere on your computer. It's going to be converted into binary. And in case you don't know what that is, we're just going to do this very quickly. If you need a more thorough look at how this goes, you can look at videos on YouTube. There's actually videos of me doing this for the discrete math students as well. So let's say you want to put 30 in binary. First of all, what's binary? Binary is representing things in terms of the presence or the absence of powers of 2. So I want to look at powers of 2 and say whether or not they need to be summed up to get to 30. So what do powers of 2 look like? 2 to the 0, it's a 1. 2 to the 1, it's a 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th power, that's a 16. 2 to the 5th power, that's a 32. So a 32, it cannot be in the sum for 30 because it's way too big. It doesn't fit there, but the others could be there. Is there a 16 in 30? Hell yes, there's a 16 in 30. Let's take it away to see what else fits. If I take it away, I have 14 remaining. Is there an 8 in 14? Hell yes. Take it away, we have a 6 remaining. Is there a 4 in a 6? Yes, there's a 4 in a 6. Take it away. What's remaining? Is there a 2 in a 2? Yes. Is there a 1 in a 0? No. So now these yeses and nos, they are my bits. So whenever something isn't in there, I put a 0. So the 2 to the 5 wasn't there. 2 to the 4 was. Cubed was. Squared was. 2 to the 1 was. 2 to the 0 wasn't. So now this is a 6-bit binary representation of 30. If I want it to be an 8-bit one, I put zeros in front. They don't change the numerical value at all. This is still a 30. And if someone gives me a binary representation of something, let's say somebody gives me a 10101 and they ask me, hey, what's this number? I just need to think, what powers are there? The 1 is there, the 2 isn't. The 4 is, the 8 isn't, and the 16 is. So it's 16 plus 4 plus 1. So that's a 22 in decimal. Okay? Let's check if we are okay. I don't want to talk about this for an hour if everybody's comfortable with this. Okay, so we are good with what the bits mean. The next section of the book is what do we do with the bits? So now, since all the numbers in the computer are in binary form, we can do a lot of things with them in binary form. And the first thing we can do is a bitwise AND. If you had trouble understanding the AND, the logical AND was the 2 ampersands, logical OR was the 2 bars. This is the same exact logic, we just do it several things at a time. So let's put some bits. Okay, that's my first number. Let's put some other bits. If I want to do a logical AND, but between the bits of 2 numbers, the first thing I need to do is I need to imagine the numbers having the same length so that my brain doesn't explode. Then I need to think that what I'm actually doing is a logical AND at every single bit position. So for an AND to be true, both of the inputs need to be true. So when there's a 1 and a 1, we're going to have a 1 and as a result. Sorry, 1 and a 1, it's a 1. 1 and a 1, it's a 1. When there's only 1, 1, or both zeros, those positions will all be zeros. So this is a bitwise AND. We could also do a bitwise OR. If we do a bitwise OR, we're going to use the rule of the OR. So AND is the one that wants both to be true, or wants whichever to be true. So how does the OR differ? The OR is going to have ones also in those positions that only had a single one. So 0, 1, it's also going to give a 1. 1, 0, it's also going to give a 1. 1, 0, it's also going to give a 1. And now it's important you don't imagine this as a 1 bit. This is the actual bar for the OR. So OR is going to have more ones than the AND, because AND wants both columns to be 1, and OR is okay with either one of them being 1. Then we have another option that we don't have in this logic, but we do have in the bit logic, which is the XOR, which is the exclusive OR. It's not a whichever, but it's an either or. So only one of the two can be true. If they're both true, XOR is going to give me a 0, because the XOR wants exactly one of the two to be true. So it's kind of like, imagine an intersection in the traffic. Either these guys have a green light or these guys have a green light. They can't both be having a green light at the same time. So in the XOR, we're just picking one. We don't let both of them go, but we also don't want the situation where both directions have a red light. No one's moving, no one's having any fun, nothing's working. So those are the logical things we can do with the bits of numbers. The same way as in logic, we could do the not, which was the negation, which is invert the values. We can also negate the bits of an integer. But there's a very important thing we have to remember. We need to remember that even if my number has only 8 bits, on my computer, the integer actually has 64 bits. So there's all these zeros in front. I can't forget them when I'm doing the negation. Because what's the negation going to do? The negation is going to switch all the zeros into ones and all the ones into zeros, but it's also going to switch all of these zeros into ones. So it flips all the bits, including the sign bit. Because remember, if it's not an unsigned value, one of the bits is going to say if it's negative or positive. So like minus 15 and 15, both of their bits are 1, 1, 1, 1, 1, 1, 1, 1. But then there's a special bit in front of the representation. Remember, I had 64 bits there. My stuff is here at the end, and I have a sign bit in the front. So we can now use our C compiler to figure out on my computer what's on the sign bit, what's negative, what's positive, and how do these bits look like by accessing the bits of the number. To be able to access the bits, there are two other operations that are very, very handy, that are the bit shift operations. They have a mathematical meaning. We won't get into that today because there's so much in a programming course that we can't really do the math at the same time. But believe me, in the discrete math course, we actually talk about what these mean mathematically. I have a right shift and a left shift. What do these operations do? Imagine that your bits are sitting on a table. If I push them k positions in this direction, the last k bits will fall off. So this would be remove me the last k bits, take them away. So if I take them away, the remaining integer, all the bits are going to run towards the right, and I'm going to be filled with new zeros in the front. If I do it the other way, if I, let's say, do this and a q, it means add new q zeros here at the end. So these are very helpful because now if I want to look at the bits of a binary representation, I could just always look at the modulo 2 because the modulo 2 will tell me if the number is odd or even. If it's an even number, 1 isn't in the sum and the last bit is 0. If it's an odd number, 1 is in the sum and the last bit is 1. So if I flush the bits out little by little, I can always look at the parity, the odd or even, to know what bits I had. So let's play with these things a tiny bit on the computer to figure out how they work and to look at the sign bit on my computer. We are going to use short integers in the hopes that we have less bits. Let's see if this is true. Let's make another file for this. So let's add this demo1 thing here to the repository, send it away. That was the initial demonstration of chapter 2. And then we're going to make a second demonstration where we're going to put all this bit stuff. And this is going to be all the good stuff. Okay? Let's make it a little larger. Making another main that returns a 0. Let's work first with just one integer. Let's make it a short integer. And let's put our friend 30 in there. So let's look at the bits of 30. We already know what they're supposed to be. We already know it's the 16 and the 8 and the 4 and the 2, but it's not going to have the 1. So we're expecting to see 3 consecutive 1s, and at the end we're expecting to see a 0. So let's look at those bits. How can I look at those bits? I can look at the modulo 2 to see the last bit. So let's print out a modulo 2 just to see the very, very last bit, which is going to be the 0 here. Where's my other window? Here's my other window. Let's make my other window tiny. And let's compile the second demo and print. So we're looking at the 0. That's the very last of these bits. If I wanted to look at all of those bits, I could do a while loop by pushing them one by one. So I could do a while A is larger than 0. We could print the last bit, and then we could substitute A by A removing the final bit. So now what I actually get is 0, 1, 1, 1, 1, because I'm reading it like this, 0, 1, 1, 1, 1. Okay, great. So now this is not an unsigned integer. So there is a signed bit there somewhere. And if I want to look at the signed bit, what could I do? I could first substitute A with its complement. When I substitute A with its complement, I'm flipping all of the bits. So these 4 bits will be 0 and all the other bits will be 1. What's this going to look like now? I didn't get any printout. Why didn't I get any printout? Because I made a negative A. So I can't do this anymore. I flipped the sign bit. So the sign bit, if it was before 0, it's now 1. And if it was before 1, it's now 0. So now I have to look at my number the other way around because I've made it negative. And if I look at all of these bits here, now I'm getting negative values because my number is negative, and it's never going to stop being negative. So it's just running and running and running. You see the little bar running away? So I'm getting an infinity of bits because I'm never going to run out of it because it's going to stay negative. I can't get rid of the negation bit there. So let's negate it and then make it positive. So only the sign bit is going to be flipped back. All of the other bits are left like they were after the negation. So now I have negated it, then I've made it negative, and then I've printed my bits again. And now, while it's larger than A, I'm getting my 1s here again. So the negation and making stuff negative, they're kind of like canceling each other out here. Okay, let's return to the original one and get a larger number. Let's get a 123 and start looking at the bits of the 123. So we have 1, 1, 0, 1, 1, 1, 1. And now we have to remember that these are the lower bits. This is the power 0, power 1, power 2, power 3. So we have to be careful not to read it the wrong way around. If I want to make operations between 2 numbers, it would be nice to be able to look at their bits. So let's make a little subroutine that prints the bits. It's going to print them the other way around. So let's make a inverted bits. We're going to give it a number A. Well, it's going to print the bits, and at the very end, let's make it print the enter. So that the bits come on one single row. But just remember, they're going to be the other way around. And now let's make 2 different values here. Let's make an S and a T. And now I could make that my S is the 123, and my T could be the familiar 30. And then I could do inverted bits to S, and then I could do inverted bits to T to look at the inverted bits of both of them. So I get one number and the other number, and I really, really have to concentrate on the fact that the bits are the wrong way around because we're consulting them the wrong way around. So don't think about these as the binary numbers. These are the flipped binary numbers. Now, if I want to make stuff like ANDs or ORs or XORs on them, I need to make sure that they have the same length, because I need to make the bottom bits match. And the bottom bits here are the first ones that I have, because this is the 0th power, this is the 0th power, this is the power 1, this is the power 1. So if I run out of powers before I've printed all the zeros I wanted, we could just print more zeros. So I could add here a length parameter that I want to be printing. Let's be nice and say what values they take. So while a is 0 or k is still larger than 0, we're going to keep printing and we're going to be subtracting the k. So now if I know that one of these needs 7 bits and the other one needs 5, I could ask for both of them to have a certain length. Let's put it here. I could ask both of them to have 8 bits in their representation. I could actually just pass it here that I want this one to come out as 8 and I want this one to come out as 8 as well. I save and I compile, and now they were printed in the same length. I've added zeros in front. If I want to look at how the ANDs and the ORs operate, I can now start doing that because it's going to be a nice little printout here. So if I print the S and the T, then I could print the S and T with the same length. So now this is S and this is T. S and T will have a 1 only in those situations where both rows above had a 1. If either one has a 0, we're going to print a 0 because we're now doing an AND. If I want to do the OR, let's actually print them prettier so that we can leave them in the repository. Let's print here the AND. It's a tiny bit confusing. Let's actually put it before so it's not so horribly confusing, so that it prints like that, that's the AND. Then we're going to copy this thing twice. So we can also do the OR, which is going to use the bar, or we could do the XOR, which is the exclusive OR, which is going to use the hat. So I can compile and I can execute. And now I am looking at what happens with both of these operations here. So I'm doing the 3 kinds of bitwise operators. I could also make changes here. If I want larger numbers, let's make a length of 12. And let's add 2 zeros to the end of the 30. And let's add 1 0 to the end of the 123. So adding 1 0, it's actually going to multiply the number by 2. So this one's going to end up being 246. And this one's first going to become a 60. Then it's going to be multiplied by 2 again. So it's going to be 120. So now if I compile and I run, now they look a little longer because I have more elements there. I've added a bunch of zeros to the end. So there's actually not much logically going on. If I want to make it a tiny bit more interesting, I could also increment S by 1, and I could add a 4 to T. If I do this again, S has been incremented, T has added 4. So now I get more little bits here. I'm not getting more large bits because remember, these are my little bits. These are the inverted binary strings. So if I wanted to read this as a binary number, I would have to read it the other way around. These are the big ones that would come on the left, and these are the little ones that come on the right. It's very important to remember we're looking at them in the wrong order because we're just flushing them out, pushing them off the table, starting with the little bits. So let's put this in the repository so you can play with that too. Really, really good programmers use this for a lot of things. Casual programmers don't even know what this means. So if you want to distinguish yourself as a really good programmer, you're going to pay a lot of attention to this. The exercise 2.7 would be inverting bits, the n bits at beginning position P. So it's kind of like reordering them. It takes a little fragment of bits here and it turns them the other way around. We're actually going to return to that later on in a homework, I think. These are the section 2.10, the abbreviations for operations, like what I was just doing here. The thing where I want t to be t plus 4, like writing this kind of stuff abbreviated, that's in section 2.10. Also read this. We talked about conditional expressions the last time with the if and the else, but there's a really cool thing that we can briefly try. We're going to make a new demo for it. And I call it personally the mini if, which lets us make much shorter code. And this is another thing that if you're a casual programmer, no one's ever going to expect you to do this. But if you really want to be good, you need to know what this means, and you sometimes actually will need to use it too. So let's say I have two integers, a and b. Let's give them some values, 13 and 8, for example. And then let's take a third one, c, not put any value into it. So I can make stuff like if a is smaller than b, then we could put something to like c, let's double it. And if a is not smaller than b, then we could decrement c by 1. And then we could just print the final value of c to see what's going on. Talking and writing is very difficult. C is an integer. Let's compile this. This is demo 3. I forgot the F in printf. I write a lot of Python code every Thursday, so it's very easy for me to forget it. So let's look at it. Okay, so C didn't have any value to begin with. My bad. So there's just some random crap. Compile, run again. So now C is 4. Because A wasn't smaller than B, so we ended up doing 5 minus 1 instead of 5 times 2. If I put a larger number in B, let's put an 82 in B. So now A was smaller than B, we ended up multiplying by 2. We could do all of this so much shorter. How can I do all of this much shorter? I could use the conditional expression. I could say here that C will be C times 2 in one case, and in another case, it's going to be C minus 1. And what's my condition? My condition would be that if A is smaller than B, then I want it to become C times 2. In the other case, I want it to become C minus 1. I can add more parentheses just to kind of like make it a little bit more legible. And I need to put the semicolon at the end. So this reads, if A is less than B, then C is going to take this value. If it's not, it's going to take this other value. Then we're going to put the same logic here again in a rerun. We're going to print C after here, And we're going to reset the values here so we can observe that it's doing the same thing. Sorry. Saving, compiling, running. So the first printout does the same thing as the second printout. So if you see something like that, it's just the person wanting to express this same logic, but smaller. And it's really good for example, if Z needs to be the larger of A and B, I could put that Z is, if A is larger than B, then it's A. If it isn't, then it's B. So this is very, very, very handy, very practical. I would recommend reading the precedence part, which explains to you when you have a lot of operations combined together, which one of them will be happening first. And that's all of chapter 2 that you guys need to learn. So remember, I need you to reread chapter 1 if you have any questions about it. If there's any part you don't understand, just take a screenshot and put it on the Discord channel of the course so we can talk about it. Pushing the last example to the repository. And then we're going to give a tiny glance to the exercises you guys are supposed to be answering today. So going to the course site, structured programming. We are interested in the little exercises. You will put the same email every single time. You should be able to see the points you got last week, and then you would go to the new exercise. So here, the first one is asking, what do you need to put here in terms of code to get the result? And what we need to be calculating is the minimum number of digits that we need to represent a number in a base. Have to go to the whiteboard for a tiny bit to explain what does this mean? What does it mean to express a number in a base? So when we were putting numbers in binary, we were expressing them in base 2. So if I have a number like 30, I already know I need 5 bits because it was 11110 in base 2. Whereas 30 was 2 digits in base 10. If I want to put 30, so let's say base 5, what's 30 in base 5? So how do I represent 30 as a sum of powers of 5? Well, it's going to be 1 times 25 plus 5. So it's 1 times 5 to the squared plus 1 times 5 to the first power plus 0 times 5 to the 0th power. So it's going to be 110 in base 5. So I have 30 in base 10, 110 in base 5, and 11110 in base 2. And now I want a mathematical way of determining how do I know how many digits I need. So if the base is 10 and the number is 30, I need to produce 2. I need 2 digits. If the base is 5 and the number is 30, I need the answer to be 3. It's 3 digits. If the base is 2 and the answer is number is 30, I need the answer to be 5. I need 5 digits. How do I do this mathematically? Now, what we have here are expressions in terms of the powers of something. So basically the question is, what's the power of the base that gets me to this number? So we could think about what's the next power after this? Like what's the power of 10 that's larger than 30? The power of 10 that's larger than 30 is 100. It's a 10 squared, which explains why I need 2 digits, because all the numbers that are smaller than 100 are representable with 2 digits. And since 30 is smaller than 100, but larger than 10. It means that it needs exactly 2 digits, because you'd have to be less than 10 to survive with 1 digit, and you'd have to be larger than 100, or actually equal to the 100 or larger, to need 3 digits. So since 30 is between 10 and 100, I know that it needs 2. Okay, for base 5, what are the powers of 5? We know 25, it's 5 squared. So 5 times 25, 125 is going to be 5 cubed. So if I have 125, that's again larger than a 30, which is larger than 25. So I need, for 25, I will need the 2 bits, because, no, the 3 bits, because it's the squared, the first power, and the 0th power. And for the 125, I will need the cubed, squared, first, and 0th. So since this needs 4 and this needs 3, this needs necessarily 3. So 5 to the cubed is like the upper limiting one, the same way as 10 squared was the upper limiting one. And here 10 to the 1 was the lower limiting one. And here 5 squared was the lower limiting one. If I have the power of 2, what powers of 2 is 30 between? 32 is larger than 30, and 30 is larger than 16. 16 is 2 to the 4th, 32 is 2 to the 5th. So I need more than 4 bits, but no more than 5. So I need the inverse operation of the power, because I know what power it is, but I need to kind of extract what's the exponent here. I know the base, I need to extract the exponent. So mathematically, what gives me the inverse of an exponent? So if I know that some b elevated to some x is y, I know this. 2 to the 5 is 32. And now I need to recover the x. I know the y, but I need to recover the x. What do I do? The logarithm base b of y will return me the x, because it's the inverse operation. If b to the x is y, then log base b of y is x. So I need to do a logarithm. And the logarithm of what? I'm interested in what's the next power. So I want to take the logarithm in the base, and then I want to round it upward. So basically, I want to know what's the previous power that I reached, and then I want to add a 1 to it. How do I do this in C? What I will be doing is I will be taking the logarithm, then after I've taken the logarithm, I get rid of the decimals, and after that, I will add a 1. Let's take another terminal for a tiny little bit so that we can look at how to do this in C. It would kind of be cool if you guys already knew how, but I'm very scared because a lot of people didn't turn in any homework, that you might not have been practicing and you might actually not know how. So let's look at it. Let's call this homework intro. What we need first of all is a new library. It's the math library. Your reference card says it's called math.h. I'm also going to put the printing so we can actually look at the printing. Let's make it return 1. So I'm interested in the logarithms for the numbers that we were talking about. So we had the 30, and for the 30 in base 2, we needed a 5. Come on. Whereas for the 30 in base 5, we needed a 3, and 30 in base 2, we need base 10, sorry, we needed a 2. So now let's try to get this number to come out of our math. So let's make an int x, and let's try to make the magic happen in that x. What do I need to do to the x? So I knew that the x needed to be a logarithm of the number that we're interested in. And the number that we're interested in is our 30. I'm actually going to put it in a variable. The number is always going to be a 30. And the base is going to be switching. First, the base is going to be 2. And we're interested in the logarithm of the number. We need to put it in base 2 in a bit. Let's print out here the base. It's always going to be b. Then we're going to switch b to 5. We're going to switch b to 10. Here we're going to be printing our number n. And the first thing we're going to try to do, this is simply not going to work as intended because there's nowhere to put the base of the logarithm yet. I'm just taking a log n, and I don't really even know what base we're talking about because I haven't looked at the documentation. Oh, I'm sorry, I haven't changed to the computer. I will change now. So let's compile this thing. And let's run it so we can look at the number of the logarithm. It would actually be better education to compile it with the -lm because I'm loading the library for math, but modern computers are pretty good at doing it on their own. So now when I do the log of n, I'm getting a 3. First of all, the log of n, since 30 is not a power of any of these numbers, it's going to end up being a decimal number. So we could look at it as a float to get a better grasp of what's going on. Compile and look at it as a float. So it's a 3 point something. Well, we had already agreed that we needed to get rid of the decimals. So if we don't want the decimals, we could round it to the floor, meaning take the decimals away. So I can make it give me a 3. Now the question is, what's the base of the logarithm that we are getting from the library call? Let's look at our reference card. Let's find the math one here. See if it says anything about the logarithm, exponential and logs, and then it says 2 power. So we are going to have to suppose that the logarithm we're looking at, it can't be base 10 because it would have to be 2 something. So we have to suppose it's a natural logarithm. You should have learned at some point in high school, in preparatoria, that the natural logarithm uses base e, and e is 2 point something. We don't want that. But you should have also learned that if you want to change the base of a logarithm, what you can do is normalize by the logarithm of the base that you're normalizing with. So I need to get rid of this being a base e logarithm. I need it to be normalized. So let's get a floating point normalizer. Let's call it BC for base change. I'm actually interested in, let's take the formula from here, change base logarithm. So this must have happened at some point in high school. The formula is here. If I want log B of A, and I only can take log D, I need to take log D of A normalized by log D of B. So if my D now is the E, I don't actually even need to know if it's E. I just need to always divide by the logarithm of the base that I actually want. Let's take a little screenshot of this. put it on our Discord so we don't forget, and go to it here. So if I want to normalize something, I can take the logarithm of the base. But since my base is going to be changing, let's put it here inside. It's the log of the n divided by the log of the b. So now anytime I switch b, I need to recalculate the logarithm. Compile, execute. So now I want 5, 3, 2, and I'm looking at a 4, 2, 1. This is a very easy fix. So once I've taken the logarithm and I rounded the decimals down, I just need to add a 1 to whatever I needed to output. So now I'm getting 5, 3, and 2, exactly like I wanted. And since I know it's an integer because I am rounding it with the floor, I could return this to AD. I could return the x to be an integer, and I just need to be a nice person to cast whatever comes from the floor to tell the compiler I know it's a whole number and I want to put it in an integer variable so that it doesn't complain. So now I have a way to calculate how many digits do I need. So now I just need to plug that math into here. I'm not going to write it here because you guys are just going to copy. So you're going to find a way to what expression needs to be put here so that we are actually printing the correct number. In the second one, this is related to the thing of the book that I mentioned. We're going to have an arbitrary integer here. It's going to be a non-negative value. We're going to have another arbitrary integer here that's going to be a bit position. And what we're going to do is we're going to calculate a y in such a way that we take the bits of x, then we go to position k and we force that bit to 1, and we go to position k divided by 2, integer division, and we force that bit to 0. I'll go to the whiteboard briefly to talk about how to force bits. So let's say I have a binary string. And I really need this position to become 1. What's the easiest way to make that position to become 1? So now let's remember the positions are indexed with 0, 1, 2, 3, 4. So what I would do here, I would first take a variable that's worth 1, an integer variable that's just a 1. I want here to be a 1. So what I'm going to do is I'm going to push this thing k positions. So let's say I had an int k that was a 4. So if I push x by k positions, what's x going to look like? It's going to be a 1, and then there's going to be 1, 2, 3, 4 zeros. So now if I put that 1 and the 4 zeros here on top of this thing, I can now do a logical operation to flip this bit to 1. Because now remember, all of the bits we're not looking at are zeros. So if I do a logical OR between the original number and my new thing, these things we would call them masks. I'm calling this thing a mask as a programmer. If I take the OR between them, in the result, I'm going to have all the original bits, but this bit here, it's forced to 1. It's going to be 1 in the OR, whether or not it was a 1 in the original one. So that's how I force a bit to be a 1. I take a 1, I push it to the right position, and then I do an OR. Let me take a photo, if I could figure out where my iPad is. I have found the iPad. Now I just need to find this class's Discord channel. Let's take a bit picture here. Reflection of the window is kind of bad. Okay, so here in this picture, I am forcing a bit to be 1, because whether or not it was 1 to begin with, if it's 0 or if it's 1, after I take the OR bit with this mask, I'm going to have a 1 regardless. So how would I do it the other way around? If I want to force a bit to be 0, what do I need to do? So let's say I have my original stuff here, and now I want to force this bit to be a 0. I'm going to again use a mask. I'm going to go to the position I want to go to. Indexes go 0 to 1, so my K is 2 now. I'm going to make my mask. My mask is going to be a 1, 0, 0. And remember, all of these other things are going to be 0. What logical operation do I need to use to clear this bit out, to force that bit to be 0? What do I need to do? Write in Discord or write in Twitch. I don't care where, but write somewhere. What's the thing that I need to do? It can't be the OR, because we already used the OR to force the bit to be a 1. Making an AND would be a horrible idea, because it's going to clear out all of these other bits too. So even though nobody's actually paying any attention to what I'm doing, the obvious answer, someone's writing, wonderful. Someone's listening to me still. If it's not an and it's not an or, what's the thing we're going to do? He stopped writing. He's writing again. And he stopped again. The suspense is killing me. But seriously, what we are going to do, we're going to do a XOR. Because since all the other bits are 0, all of these other original bits will survive. The only bit that's necessarily going to be, actually no, if I do a XOR, I only get a 0 there if there was a 1 to begin with. And if there wasn't a 1, if there was a 0 there, I would actually flip it to a 1. So if I want to make sure it's a 0, I would first have to check whether it's a 0. And to check whether it's a 0, I could do an AND with the mask. Because if the AND with the mask gives a 0, then I know that it was a 1. And then I would do the XOR. And if the AND with the mask gives a 0, I know it's already a 0. So then I don't really have to do anything to it if I want to force it to 0. So XOR is really good for flipping the bit to what it wasn't. OR is really good for forcing the bit to be a 1. If I want to force the bit to be a 0, I will check the AND, and then if it isn't 0, then I will do the XOR. So it's just a little tiny bit of thinking and careful reading. Okay. And everybody's going to have a different value of K, and the X is going to be an arbitrary value, so you can just try it out with different values of X. In the last one, you simply need to use that little interrogation sign if to make it print log of P if logarithm of P is larger, and square root of Q as SQRT of Q when it's not, and a new line at the end. So this is a really easy thing. You're just going to use the thing that has the interrogation and the colon. After you've done those, you're going to make a program that prints out binary strings to prime numbers. You're going to make all the binary strings to be of the same length, and you're going to have to figure out how to flip the bits in the code that I made so that they will actually come out in the correct order. Let me add this thing to the repository before I forget it. Then I will go one more time to the whiteboard, which you guys are still looking at. This was what? This was the log demo stuff. Because we still need to talk about the prime numbers, because the exercise is talking about prime numbers. Okay, so just to make sure everybody's on the same page on what's a prime number, it has to do with divisibility. I'm going to write some integers here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. A number is a composite if I can represent it as a product of other numbers. So, talking about integers here. 4 is a 2 times 2. So 4 is not a prime number because I can represent it by multiplying together other numbers. 6 is a 2 times 3. 8 is a 2 times 2 times 2. 9 is a 3 times 3. 10 is a 2 times 5. So if you can represent it as a product, it's not prime. The numbers that you cannot represent as a product, so that means the numbers that are only exactly divisible by 1 and the number itself, those are prime numbers. 2 is the only prime number that's even. No other even number can be prime because they're all divisible by 2. So these are primes. So what you need to do for the homework, you need a subroutine that figures out whether or not a number is prime. And you can do exactly what I was doing here. You check if it's divisible by 2. If it wasn't, you check if it's divisible by 3. If it wasn't, don't check by 4, because if it wasn't 2, it's not going to be 4 either. Check if you can divide by 5, etc. And if you can get all the way to the number itself without finding anything that divides it, then it's prime. So we want one subroutine that checks if a number is prime. Then we want another subroutine that gets the bits of that number, puts them in the right order, opposite of what I did today, and puts the zeros in front so that they all have the same length. So that then your main routine is going to keep looking for prime numbers until it finds a total of k of them, and it's going to print out the binary representations of those prime numbers. Please post on Discord any partial progress you have so we can discuss it. Remember to first answer the 3 mini exercises before you start trying, because you really need those skills to be able to survive the homework. I'm also going to take a picture of this just in case as a reminder. All of this stuff is really easy to Google, like stuff like what's a prime number? How do I know if a number is a prime number? Remember in your code, please put like comments that explain what are the sources that you're citing, like what are the websites or books that you have been looking at. Remember to avoid copying code. It's okay to read other people's code. It's not okay to copy and paste it. And if you're looking at other people's code, always remember to include a comment that says where you got that information from, so that there won't be any confusion if your code happens to resemble somebody else's code. When you answer the mini exercises and you grade them, like you just write whatever here, you grade. If it's mistaken, it's going to complain to you, and it's going to give you hints on how you're actually supposed to be solving the exercise. So I would hope you guys could do that relatively soon. Remember that all of my code is at my GitHub repository. There is a lot of other examples in addition to the ones we've been looking at today. You can go look at all of those. If you have GitHub trouble, ask on the GitHub channel. You can ask anything related to the math or the programming aspects here on this very channel. If you have trouble understanding concepts and you can't find a good tutorial, I will find it for you as well. One easy way for flipping the bits when you get to the part of flipping the bits is that you could use a character array or an integer array, and you could just fill it in the inverse order. That's an easy way to flip things around. So none of this will be horribly complicated, but you do need to dominate the concepts of the first chapter and the second chapter. The second chapter didn't have a lot of new stuff. It just had a lot of clarifications on how the stuff we had seen in chapter 1 actually works. So let me stop the stream on Twitch. I'll give you guys the link to that. I will also give you guys the link to what we did in the grading session on Discord. That's the one that's going to go unlisted on YouTube. And I'm very eager to see you guys try to work on this stuff during the week. Ask on the channel. Please don't ask me in private messages. On the channel, please. If you can during the daytime, but if you have to ask at 3 a.m., well, maybe one of your classmates will answer you. Don't try to do it everything at once. Don't try to suffer alone. Do things little by little and ask for help, and you are going to learn to program. There is no shame in asking, but it's a very, very stupid thing to just suffer by yourself. So I'll catch you guys next Thursday. Please practice and please talk on the channel about what's going on with your code.